My name is Dr. David Boyce, and for 30 years I have been an astronomer. My PhD is in astronomy and astrophysics. Welcome to this, the first of a series of videos that will take you through GCSE astronomy. Our journey through this astronomy course starts here with the Earth. Now, the Earth is the largest of the 4 terrestrial planets. Its diameter is about 13,000 kilometres, and it is the basis of everything we know. So let's take a look at the Earth. A few years ago, I launched a weather balloon to the edge of the stratosphere. It was only then that I really got a sense of the fact that the Earth is a planet. You can see the blackness of space above, and when the camera angle is just right, the curvature of the Earth. But what do we know about this, our planet? That which makes Earth unique amongst the terrestrial planets is the fact that its surface is so varied. 70%, in fact, is covered in water, the oceans. But even amongst the land masses, there's great variation, from deserts, mountains, glaciers, and ice caps. The Earth's surface is known as the crust, and this ranges in thickness between 0 and 70 kilometres. In places, like on the continent, the crust is really thick, and it's much thinner underneath the oceans. The crust is where the tectonic plates are. Being fractured, these large areas of crust over millions of years can move relative to each other. On this here, the crust is demonstrated by this thin little edge here. That on the scale of this model, the crust would only be as thick as a sheet of paper. Beneath the crust, there is this region here called the mantle, and it actually only extends to about halfway down, but because of how spheres work, it actually represents 80% of the volume of the Earth. It's full of hot, silicate-rich rocks, and very slowly over time, these rocks can shift in position relative to each other. It is in fact like a convection current occurring within the rock that is moving around the tectonic plates on the surface of the Earth. Underneath the mantle, this region here, the outer core, might come as a surprise. For the temperature and pressure are so great down here that the actual rock has become a liquid. It's basically melted. And so here is a giant 5,000 Kelvin ball of liquid magma. It is in this magma that currents of charged particles generate the Earth's magnetic field that we can detect on the outside with a compass. Indeed, what is surprising to a lot of people is inside that liquid outer core, there is a region in the middle that becomes solid once more. You see, with the increasing temperatures, you'd expect that it's melted and then it couldn't become solid again in the middle, but actually what's happening is, under the weight of all of these outer layers of the Earth, the pressure is increasing and increasing, and the pressure starts to win in the very centre, that even though it is hot enough to be liquid, not at the extreme high pressures that this centre is under. In fact, though the temperature is about 5,500 Kelvin, the pressure is higher than would allow it to remain a liquid. So in the centre there's this little ball made mostly of iron and some nickel. And actually that ball, it spins, and it spins totally at a different rate to the rest of the planet, which is amazing, because what's happening is you've got the planet rotating at one rate, and then there's this little ball in the middle of the magma sea that is spinning significantly faster. And I find that amazing. And it's also that motion that sustains the Earth's magnetic fields that we can detect on the outside. The Earth rotates once on its axis every 24 hours. That's what we call a day. And this line that goes through the North Pole and out of the South Pole, that is the axis around which the Earth rotates. Now the Earth has been rotating for its entire existence, even when the Earth was a lot hotter and more liquid than it is now. It has cooled down over time. When it was more liquid, that rotation had the effect of sort of expanding out the middle of the Earth around the equator and squashing down the poles. It means that the Earth has basically set in the sort of shape of a, Satsuma. So the actual technical name for this shape, a sphere that is squashed along its rotational axis, is an oblate spheroid. Some of the planets in the solar system are oblate spheroids, like Jupiter, for example, because they rotate really quickly. So why is the Earth an oblate spheroid? Well, I've got a balloon with some water in, and I've tied it onto the end of a nail that I've got in this drill attachment here. As I turn this on, what I'm going to do is I'm going to speed up the rotation rate. And you can see it's physically changed shape. That's amazing!